As we continue our journey through WAN connections, we move from the leased line into packet switch networks, of which Frame Relay is one of them. We're going to take a look at what Frame Relay is all about. And when I went through the CCNA many moons ago, Frame Relay was one of those concepts that just baffled me and I was so confused on. And I think it was just because I had a bad starting point. I really just didn't get the big picture of what Frame Relay was all about. So that's how I'd like to start. I'll give you the big picture of why Frame Relay, why this technology is out there. We'll then get into one of the big concepts of Frame Relay. We'll look at the terminology and especially DELCs. That's the addressing that Frame Relay uses. And finally, we'll look at Frame Relay design options. Frame Relay originated as a result of service providers monitoring leased lines. Leased lines used to be the way to connect, and people would just buy dedicated bandwidth between their locations. Now, the benefit of that is it's your bandwidth. You always use it all the time. The problem is when that bandwidth is not being used, because nobody uses 100% of their bandwidth 100% of the time, it's just sitting there. So the way I see Frame Relay is kind of the same way I see, well, Fuddruckers. If you've ever been to the restaurant Fuddruckers, it is a 50s hamburger restaurant, and they have milkshakes that dreams are made of. They have this massive, when you order a milkshake, they bring you this massive glass cup. And in that glass cup, it's glass and it's got the lines and all that. They just top it off with like strawberry milkshake to the very top. And that you'll never finish that glass cup, but almost to joke with you, they give you this silver can that is all of the extra milkshake stuff that they couldn't fit in the glass cup. So if you were to drink both, you would most certainly die. So here's the idea behind Fuddruckers entrepreneurship. You can go to Fuddruckers and order a milkshake and then take that milkshake, stand up on one of the tables and say, "Ladies and gentlemen of Fuddruckers, fellow patrons, I have ordered a strawberry milkshake. We all know if I drink this milkshake in its entirety, I will most certainly die of heart disease by next year. So what I propose is this. I will sell straws into this milkshake for we'll give you the larger straw, the McDonald's size straw for 25 cents, and you can tap into my milkshake with me for 25 cents with a McDonald's straw. Now if you're on a budget, I'll give you a normal straw for 10 cents. And if you are on an extreme budget, you might be married. I'll give you a coffee stir for a penny, and you can tap into my milkshake with this coffee stir. So what you do is you sell all these straws, make a bunch of friends, make all your money back on that milkshake, and maybe even a little profit, and you get some milkshake yourself. That's the idea behind Frame Relay, and that's the idea behind packet switch networks. Service providers watched these leased lines and said, there's bandwidth that's not used. Tell you what, let's do this. Let's make a big cloud of bandwidth, gigs and gigs of bandwidth inside of this cloud. And what we'll do is have this in somewhat of a pool. We will sell straws through this cloud, or that can connect different sites together. If somebody is not using their bandwidth in Frame Relay, chances are somebody else is. And that's the whole idea behind this kind of network. Now, Frame Relay is part of the packet switched class of networks, of which X.25 was the first one. Now, it's evolved over the years. X25 became Frame Relay, and then Frame Relay became ATM. And then ATM and all these have kind of been transitioning over the last few years into a technology called MPLS. But it all works in a similar way in that you have this big blob of bandwidth, and if you're not using your bandwidth, someone else is. Now, the power behind that is the service provider can sell you cheaper connections, because they don't have to dedicate all that bandwidth to you. The service provider can also over provision that cloud. Like let's say there's, we'll say 2 gigabits per second of bandwidth available here. The service provider can sell, we'll say 3 gigabits per second to all of its customers, because in all their studies and monitoring and testing of these networks, they have determined that, with this ratio, they are able to sell this and still meet all the customer demands, because, again, not everybody's going to use all their bandwidth all at the same time. I guess you could also think about Frame Relay as a bank, and in the sense that the bank lends out more money that it has because they're making the bet that not everybody's going to come withdraw all their money at the same time. If they did, the bank would run out and not everybody would get their money. Same way with bandwidth. So half of the game in Frame Relay is just getting used to the terminology and how these connections work because it's very different than Ethernet and even leased lines. The first term that we have is committed information rate. This is the bottom line, the minimum bandwidth that the service provider guarantees you. So if let's say I had this office here in Arizona, I might sign up for a committed information rate, a CIR of 500 kilobits per second. Now, when you think of a minimum, that's the bottom line. A lot of times in Frame Relay, you can actually burst. It's known as bursting above your committed information rate if the bandwidth is available. Now, there is kind of a common line of courtesy that if you're always boosting above and always using more bandwidth, the service provider will monitor that and let you know and say, hey, you really need to start paying us more money to up your CIR because you are continually using more bandwidth than what you're paying for. So that comes back to the local access rate. The local access rate is physically how fast that circuit can go. And this is one of the big differences between Ethernet. When we think about Ethernet, we think of things like fast Ethernet. When I plug in that cable can go 100 megabits per second. And if my computer can send 100 megabits per second, the cable can handle it. Well, therein lies one of the big differences in Frame Relay. You might have a local access rate of 2 megabits per second, but a CIR of 500 kilobits per second. So even though the physical cable can handle 2 megabits per second, you're only paying for 500 kilobits per second, and you should be configuring your router to only send at that rate unless you have some kind of bursting agreement set up with your service provider. So that's one of the first differences, is a logical and physical speed mismatch. Now down below you see Local Management Interface, or LMI. LMI is the language you speak between your router and the service provider. LMI lies right here. This is a signaling protocol that the service provider can use to send you statistics on the line. It can tell you, the status, the relative quality of your transmissions, if it's dropping packets. You can even use LMI to send DELC information, and that's one of the big terms next. You see DELC. Ethernet uses MAC addresses, right? You send from this source to this destination. Well, in Frame Relay, you use DELCs. That's the Frame Relay equivalent of MAC addresses. They work quite a bit differently than MAC addresses, or I guess you can think of them as backwards, but we're going to talk about that on the next slide. So I don't want to get too deep into DELCs. For now, you can just think that every single one of these sites is identified by a DELC, a data link connection identifier that allows it to communicate. Now you notice I put little dotted lines through the cloud. It's almost my instinct. I wasn't even thinking. But those little dotted lines represent our last term here, which is Permanent Virtual Circuit, or PVC. When you sign up for a Frame Relay service provider, you will typically have, let's say in Arizona, a single connection to the cloud. Serial 0/0, we'll say. It's connected right here to the service provider. Now, once you get into that service provider, you can pay for one or more PVCs, which dictates where that service provider can take you to. So I might buy in Arizona a PVC that goes to Florida. Now, every single one of those PVCs has a CIR. Now we're getting weird, right? So for example, I could have a PVC from Arizona to Florida that has a 500 kilobit per second CIR. Now, I could also buy a second PVC from Arizona to California that has a 800 kilobit per second CIR. So total, if you look at that, 500 plus 800, that's about 1,300 or 1.3 megabits per second of bandwidth that I have there. And as long as I don't exceed my local access rate, I'm okay. I can, keep bundling all these together. Now, every single one of these PVCs has a reoccurring monthly cost. So the more PVCs you have, the more you're going to pay for your frame relay circuit. And because of that, a lot of times companies will just have as few PVCs as they can. Like what you see right here. Arizona is connected to California, Florida, and we'll say Texas. That's our three PVCs. But Florida is not connected directly to California. It has to go through Arizona to get there. This is actually known as a hub and spoke frame relay design. Again, we'll talk about that more later. The main thing I want to focus on is the PVCs. This is a shift, a paradigm shift for many people, because if you're used to leased lines, a router connected to another router, you can think of, serial 0 goes to the Texas router, period. It doesn't go anywhere else. But in Arizona, serial 0/0 could be the same interface you use to reach 3, 4, 5 different offices, depending on how many PVCs you're paying for. So it's a little shift. Think about frame relay more so like VPNs, if you can think back to that WAN connection video, where I said you've got one physical link, but it can connect to many different sites across the internet. In the same way, frame relay can have one physical interface that's connected many places. Now let's dig a little bit deeper on that concept of DELC. How do DELCs work? This, to review just from the previous slide, is the addressing that frame relay uses. It's like a frame relay quote-unquote MAC address. The reason DELCs can get so confusing is because we're used to the Ethernet world. If you've got two devices that want to communicate using Ethernet, we have a source MAC and we have a destination MAC. When this computer wants to send some data to that computer, it sends from this source to that destination. That's what we're used to. Frame relay flips that whole thing on end. DELCs are known as locally significant, and let me show you what that means. In Missouri, I might have DELC 200. Texas might be DELC 300. California might be DELC 400. Now, Arizona might have DELC 100, 300. Well, hang on. Let me not do that yet. I'll do 500 and 900. Okay, these DELC numbers can be any number from, well, technically 16 to about 1024. So any number in that range. Now, again, what we're used to is this MAC address concept. So we would think, well, when Missouri sends to Arizona, we're coming from a source of 200 and going to a destination of 100, right? No. In frame relay, it's exactly the opposite. When Missouri sends some data to the frame relay service provider, if it wants to go to Arizona, it's going to send it to DELC 200. That's the destination. The service provider will take that data through the cloud, and when it comes out in Arizona, it comes out on DELC 100. Whoa, weird. That's how frame relay works. The best way I can describe this and the best analogy that I can paint for you is going to the airport. This weekend, my wife and I are flying out to California for a little Christmas vacation. And we're going to go to the airlines, and when we get there, we're going to be boarding on Southwest Airlines, and we'll look at the little monitor. It'll say, you are departing out of gate B23. So Sue and I, that's my wife, will go to gate B23 with our little infant Isabella, and we will walk up to that gate and sit down in the terminal, and plane will land. We'll board the plane, fly through the air. Isabella, Sue, and Jeremy are all in the plane, flying through the air. And when we get to California, we step out, and I happen to turn around me, and I notice that I just walked in on gate A5. Whoa, freeze right there. Did some kind of trickery happen in the air? I know you're thinking, maybe, maybe there was some kind of strange thing that happened. No, not at all. All that happened is you left out of one gate and you landed and arrived on another. That's the concept of frame relay. When you're sending from, we'll say, Missouri to Arizona, you leave on DELC 500. When you send some data, it's going to that destination DELC, or did I say 500? I meant 200. You're leaving on DELC 200, flying through the air, fly through the cloud, and then you land and come out on DELC 100. If Arizona wants to get to, we'll say, California, it will send data to a destination or leave on DELC 900, fly through the air, and come out in California on DELC 400. Now, with that in mind, let me show you something that might just blow your mind. It might not, but it might. Sometimes service providers will do something like this. California has Delcy 300 to get back to Arizona, but so does Texas. And while we're at it, let's go crazy. So does Missouri. Missouri also use Delcy 300 to get back to Arizona. You might be thinking, everything in your TCP/IP body right now is like you can't do that. That's an address conflict. Or you're thinking of MAC addresses. You can't have the same MAC address. Well, that's the difference of Delcy's. And now we come back to this. Delcy's, oh no, I lost my underline. Delcy's are locally significant. That means that Delcy 300 in Missouri means something in Missouri that could be very different than what Delcy 300 means in Texas. You could even do this. Why not? Let's go crazy. In Arizona, we also have Delcy 300. Wow. The reason this is possible is because Delcy's are locally significant, which means when you send data in Arizona to the Arizona service provider on Delcy number 300, they have a little map in their Arizona, notice I'm emphasizing, routing table that says if they send Delcy 300 in Arizona, that needs to go through our network, blah, 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 all this stuff, happens in the network, and then come out on Delcy 300 in Missouri. So the Delcy's are locally significant in that 300 in Arizona means something very different than 300 in Missouri, Texas, and California. Now, you could not, I'll stop the madness right here. You could not do that. Have two 300s on the same interface in the same location, because that now you've confused it. It's two 300s in the same place. You've lost your local significance. So that's the idea of what's possible with frame relay and how these Delcy numbers work. Hopefully that gives you a pretty clear picture of how this addressing works. You just have to remember sending to a Delcy is locally significant. Now, the last thing I'll say, I was trying to think of where I was going next. Last thing I'll say is a lot of questions come in of what really happens in that cloud. What I'll say here is what happens in the cloud stays in the cloud. Let's just leave it at that. I'll tell you, technically, behind the scenes, when you get into that service provider, they tear this Delcy off and throw it away. They rip off the whole frame relay header, and as you go through this network, you're probably hopping from router to router to router to router, and coming out in Arizona. If you were to do a trace route, though, you never see any of that. It's all hidden to you. That's why the cloud is invisible. You just see that you came in, the packet's like, whoa, it just totally gets its headers torn off, spun around, turned back around, ends up walking out in Arizona, never knew what hit it. Now, because of the way PVCs work, there are really three ways that you can design your frame relay network. You can see that the most common way, because it's the cheapest, is the hub and spoke. That's where you have one hub, right here, you can see Arizona, and all the other offices are spokes. So there's my hub. Now, the beauty of this is the cost. It is the cheapest way to get all the offices together. The disadvantages are, number one, you've got a single point of failure. If Arizona goes down, everybody goes down with it. Second thing is, now that we are getting these voice over IP networks, we also have to consider something known as delay. What delay is how long it takes a packet to get from one place to another. Now, with data, delay didn't really matter. You could send stuff, and as long as the bandwidth was there and it got there eventually, it would be fine. It might just take the bar a little longer to go across the screen if there's a huge delay. But in voice, let's say you've got a phone over here in Missouri, and he wants to talk to a phone over here in California. With frame relay, if you have to go to California, you have to go through the hub, Arizona, get processed, loop back around, and then be sent out to California to reach that phone. That can cause some considerable delay, especially if the hub is pretty far away from these two spokes. Now, the longer delay you have, the worse quality voice over IP call you're going to end up having. And you might have calls that break up, calls where it's just unnatural. You're trying to talk to somebody and it's so long before they respond, you start overlapping. It's not good. So we're starting to see some significant disadvantages nowadays with this hub and spoke design. So you might flip on the other side and go, well, let's do a full mesh. Full mesh is where every office has a PVC to every other office. You can see Missouri has full connections to Arizona, Texas, and California, and so does Texas, and so does California. This is the ideal design, but now you're getting into the big disadvantage of cost. This is the most expensive design you can have, and the more offices you add, the more it grows exponentially because then you have to link everybody to this office and add redundant connections and so on. So the cost keeps going up in the full mesh. So what people usually end up negotiating on is a partial mesh, meaning your critical sites, like Arizona in this case, has full connectivity to all the other offices. California's got a redundant link between Texas and Arizona, but you can see Missouri, maybe, these guys just play online games all day anyway, so they just have a single PVC. When layoffs come, just make sure that you're not the single PVC location, because they are not the critical ones. So that's usually a good compromise between redundancy, performance, and cost. The last thing we'll talk about is the logic or the design idea when you're configuring your interfaces for frame relay. And this leads into the next video on frame relay configuration. You can design your network in either a multi-point fashion or a point-to-point fashion. Now, multi-point, in my opinion, is a poor design strategy. The reason I say that is because all of the routers are on the same subnet. Now, it makes the routers believe as though it's kind of like an Ethernet network where Arizona can send out a message and, Missouri, Texas, and California will get it. But the problem is, you can see only Arizona can do that. If California sends out a quote-unquote broadcast or a message, only Arizona receives it because there's only a single PVC between those two offices. So in a multi-point design, all of the routers are on the same subnet. Notice, everything starts with 192.168.1 here. They're all the same subnet. You have multiple DELC numbers mapped to the same interface. So in Arizona is the only one here with multiple DELCs, maybe 200, 300, and 400 are what connect it to the other offices. We would map those to this interface and it would all go out the same direction. Lastly, this is known to cause problems with split horizon. Now there's your pop quiz. Do you remember what split horizon is? It came back from when we were talking about distance vector and link state routing protocols. There's a specific video earlier in the series that is distance vector versus link state. In there, split horizon was introduced as one of the loop prevention mechanisms. It stops loops from happening in your network. The way it did that and the way the rule works is it says never send an update back in the same direction or out the same interface that it was received from. So if this router on the right was advertising 10.1.1.0 to this router could never turn back around and advertise 10.1.1.0, otherwise you could potentially cause a loop. Well, that loop prevention mechanism causes problems in this environment because Missouri might need to send a route update. We see the frame relay portion, but we also have networks behind here. Maybe Missouri has the 172.16.1 network back there on its LAN. Well, it will send a route update to router Arizona through its DELC, and Arizona receives that update and adds it to the routing table that Arizona now knows how to reach Missouri's network. But then the problem is split horizon tells Arizona, do not send that update back out the same interface you received it on. Are you getting my points here? Serial 0/0, it was received on, so it never turns around and sends it back out. So Texas and California will not hear about the 172.16.1 network update. So the solution in a multi-point design is to turn it off. Meaning, I shut off split horizon, a loop prevention mechanism, in order for this network to work correctly. My preferred method of configuring a frame relay network is in a point-to-point design or point-to-point configuration. And I want to make sure that I emphasize before we go any further into this that this is something that you choose as somebody configuring a Cisco router. You choose whether you want to use a multi-point configuration or a point-to-point configuration. It's not something you have to coordinate with a service provider on or say, explain to them, oh, this is how I'm going to do it. Can you please set me up this way? This is something that you do. And in a point-to-point design, all the routers are on different subnets. You can see that I have Missouri on 10.192.168.1.2, which connects to Arizona down here, 192.168.1.1. That's the subnet between Arizona and Missouri. Arizona to Texas, 192.168.2.2 over here. And I'll explain this shindig in just a moment. A point-to-point design emulates, as if I were to draw this out, as if Arizona had individual leased line connections to each one of these places. Whereas multi-point makes Arizona think it's kind of like it has an Ethernet network and everybody's on this same shared subnet, which causes a lot of strange and odd problems that you'll have to configure. So point-to-point is just a lot more logical. The way you set it up is create a point-to-point sub-interface for each peer. Notice, in Arizona, I have 0/0/0, which is the physical interface, and there is virtually no configuration underneath that interface. What I do is I create a sub-interface, serial 0/0.100, 0/0.200. These sub-interfaces work in the same fashion that they do if you can think back to our VLAN routing. Remember our router on a stick with VLANs and we created the sub-interfaces, one for each VLAN? Well, it's the same way here, but we have one sub-interface for each DELC. Now, all these other routers only have one DELC back, so you notice I didn't set up a sub-interface on there, but if Missouri needed to connect back to California and we added a second DELC, I would then go ahead and remove this config from the physical and create two sub-interfaces, one to come back to Arizona and one to go down here to California. So point-to-point design is allowing you to create a separate logical interface or sub-interface for each one of those connections that you have. This eliminates the problem with split horizon because when a routing update comes in, the router sees it coming in serial 0/0.100. It doesn't break the split horizon rule to send it back out serial 0/0.200 and .300 that will reach both of those DELCs. So point-to-point design, in my opinion, is the best way to go. In the next video, I'll walk through the configuration of both a multi-point and a point-to-point frame relay network, and I'll let you decide which one you think is the best, with no subtle hints from me. So what we saw in this video was the big picture. You can see frame relay is very different than any other network type that we've talked about so far. We saw a lot of the terminology like committed information rate being the logical speed you can go. Local access rate is the maximum physical speed you can go. DELCs being the addressing. LMI being the language between you and the service provider. So all of those things go together to build this frame relay concept. We then took special time to look at DELCs because the addressing works very different than any of the addressing we've seen so far. Instead of going from a source to a destination, you essentially leave on one DELC and land on another, very similar to an airport. Last but not least, we looked at our frame relay design options where we had the full mesh where everybody had a PVC to everybody, a hub and spoke, which is exactly the opposite. You have one hub with links to everybody, and then a partial mesh configuration where we have key sites that have multiple circuits and the not so key sites only have a single. I hope this has been informative for you, and I'd like to thank you for viewing.